Hello friends. So today we are going to discuss three questions, and these three questions are from the year 2013, and one question is from the 2000 mains, and two questions are from 2000 advanced. So we have total of three questions. And the first one, which was asked in the year 2013 mains, and it says that two short bar magnets of length 1 centimeter each have a magnetic moments of 1.2 and 1 ampere meter square respectively. They are placed on a horizontal table parallel to each other with their north poles pointing towards the south. They have a common magnetic equator and are separated by a distance 20 centimeter. The value of the resultant horizontal magnetic induction at the midpoint O of the line joining their centers is close to. The horizontal component of the Earth's magnetic induction is 3.6 into 10 to the minus 5 Weber per meter square. So in this case, we have two bar magnets, and it says that their north pole is pointing toward the south. Okay. So let's draw an approximate figure for that. So we have the north and south direction. So this is our north and this will be our south, and we have these poles, magnets, the first magnet and second magnet, and we are going to have this as a south north as well as south and north, and the midpoint, let us suppose, is given as O. So in this case, we are going to find out what will be the magnetic field at the midpoint O between the two magnets. And the length of each magnet is given as 1 centimeter. Let us suppose this is our first magnet and this is our second magnet. So we can write that magnetic moment which is given to us for the first, let us call that M1. So M1 is our 1.2, and we have M2 for the second magnet, and that is our 1. And distance between the two is given as 20 centimeter, and the length of each is our 10 centimeter. 1 centimeter, sorry, not 10. Is over 1 centimeter. And we are also given the horizontal component of the magnetic field. Horizontal component of Earth's magnetic field BH is equal to 3.6 into 10 to the power minus 5 Weber per meter square. So the Earth's horizontal magnetic field will be in this direction, which we are going to call as BH, and we have to find out the resultant magnetic field. So first of all, let's find out what will be the magnetic field on the equatorial line. Okay, let's write the formula. You can say magnetic field on the equatorial line of a magnetic dipole and you can write this as B equatorial will be equal to mu naught upon 4 pi, and this is m upon r cube, where r is the distance. In this case it is the distance of the midpoint, so our r will be equal to 0.1 meters, and mu naught upon 4 pi is our 10 to the power minus 7. So now we can divide this equation. Let us pause equation 1 into two separate magnets. So we can say for magnet 1, we can write this as P1 is equal to 10 to the power minus 7 multiplied by 1.20 and 0.1 whole cube. So this comes close to as 1.20 into 10 to the power minus 4 Tesla. And similarly for magnet 2, B2, only difference will be in the length. So this comes 10 to the power minus 7, length is 1, and this comes as 0.1 raised to power 3. This gives you 1 into 10 to the power minus 4 Tesla. And the direction, so we have our north, south, and the direction was for BH. This will be for B1 and also for our B2. So they are all in the same direction. Therefore, all the fields will be towards the north. So the net magnetic field B will be equal to BH plus B1 plus B2. BH is our 2.56, 3.6. We have it is 3.6 into 10 to the power minus 5, and we have B1 is our 1.2 plus 1, 0, 0, and this is 10 to the power minus 4. So this comes as 3.6, and this will be over 2.20 and into 10 to the power minus 4 plus 3.6 into 10 to the power minus 5, and therefore it gives us that B will be equal to, only difference is the power, so this comes as 2.56 into 10 to the power minus 4 Tesla. So the correct option is our 2.56 into 10 to the power minus 4 Weber per meter square. So we can say option B is the correct one. Option B is correct. Now we came to the next question, and this was asked in the year 2013 as an advanced question, and it says that a particle of mass m and positive charge q moving with a constant velocity u1, that is 4I unit vector, enters a region of uniform static magnetic field normal to xy plane. The region of the magnetic field extends from x equal to 0 to x equal to L for all values of y. After passing through this region, the particle emerges on the other side after 10 milliseconds with the velocity u2, that is given as 2 square root of 3, here it should be I unit vector plus j. The correct statement is or are. So in this case, we have to find out both the direction as well as the magnitude. So in this case, you can say we have a magnetic field that extends from x equal to x equal to L. Okay. So let us draw so this is our x equal to 0 and it extends to somewhere here x equal to L, and it says that the magnetic field is normal to the xy plane. Okay. So this is our x-axis and this is our y-axis, and initial magnetic field is initial velocity is 4 of, so initially it is our u1 and the final velocity is its, you can say, that is given as u2. Okay. So let us rewrite the final velocity equation and try to sort it out. So we are given that final velocity, which is our u2, is equal to 2, and we can write this as 3I unit vector plus j unit vector. And initially u1 is only having one component, that is x component, whereas as it passes through the magnetic field there is addition of j component, or we can say it is deflected, the particle was deflected. Okay. So this is, you can say that initially motion is along I, and after passing through magnetic field there is j component, so it means that particle was deflected. Particle was deflected. Thus we can say that there is a, you can say this is consistent with either the circular motion or helical motion due to the Lorentz force, because of the presence of magnetic field which is perpendicular. So let us try to find out the magnetic field motion. You can say motion in the magnetic field, motion in the magnetic field, and magnetic field is uniform, so we can write force because of the magnetic field is equal to Q, we have here V cross B, and the force will be always perpendicular to the velocity, which results in a circular motion, and speed is a constant, only the direction is changing. And from here you can also say that for uniform circular motion, radius, which is r, is given as mv divided by q times b. Now let's find out what will be the angle of deflection by which it will be deflected. You can say, or we can also say that as it will be addition of y component, so let us suppose this is the point and where the magnetic field ends, and after that its velocity is given as u2. So we can find out its angle. Let us suppose that angle is given as theta. So we can say that the particle traverses a circular arc in the field for a certain time, and let us suppose that angle is theta. So we can say completing an angle theta, and emerges with a different direction but with the same speed. Emerges with different direction but with same speed. So let us find out what will be the angle. So you can say deflection angle. U1 is already given to us, that is our 4 times I. U2 is also given to us, that is our 2 square root of 3I plus j unit vector. So the angle between U1 and U2. So first of all, let us find out what will be the magnitude of U2. So we can say U2 will be equal to 2, this is square root of 3 whole square plus 1, and this comes as 4, and our U1 is also 4. So from here we can see that our initial velocity is equal to final velocity, okay, because the magnetic field does no work, so the velocity has to be same, only the direction is going to change. Magnitude has to be same, only the direction is going to change. So therefore now we can find out the angle. So we can say angle theta, and write our cos of theta is equal to U1 U2 divided by U1 and U2. So here we are left with only 4.2 root 3, and this is the vector notation, and the magnitude is our 4 times 4, and 4 goes with 4 and this goes by 2, so we are left with only 3, 2. So theta will be our 30 degree. So it means the circular motion subtracts an angle of 30 theta, that is 30 degree. Therefore you can say from here the circular motion subtends an angle theta which is 30 degree, or we can say pi by 6 radians. So which basically means, so we have a initial velocity in this direction, and our this is our x equal to 0 and we have x equal to L, so it will be something like this. And if we have this as a center, and if we join them, this arc will be subtending at an angle of theta which is our 30 degree. Now we can use angular velocity, that is theta is equal to omega t. Omega we already know is q by v, and that is going to help us to solve it further. So we are given, or rather we can also, our angular velocity omega is equal to qb upon m, and our theta is equal to omega times t. We substitute value of omega, we get theta is equal to qb upon m multiplied by t, and we substitute it. Theta is our pi by 6, we get this as qb m, time is given in millisecond, 10 to the power minus 2. So this gives us that our magnetic field B will be equal to, we have it pi m divided by 6q multiplied by 10, or we can say 100. Therefore we can further write it as, this will be equal to, this goes by 3 and here goes by 50. So we get our magnetic field B is equal to 50 pi m upon 3q. So we found out the magnitude, and we also you can say need to find the how can I put it, the direction also. Okay, and we are given that direction of magnetic field, we are given that charge is our positive and u initial velocity is our 4I, final velocity is 2 square root of 3I plus j, and we just also drew the diagram for this, that it's the path it takes is towards positive j direction. So we can say the particle curves upward in positive j direction. Therefore magnetic force is in positive j direction. magnetic force is in plus j, a unit vector rather, plus j direction. And now we can use the equation that our F is equal to Q V cross B, and V already we know is in I direction, and we need to find out the direction of B, but we know the direction of force. And from here we can just, you can say, draw a conclusion that our magnetic force will be, because we want that the unit vector which is associated with the magnetic field when it makes a cross product with I, or rather we can say if I makes a cross product with a unit vector of magnetic field, the final answer should be equal to J. So based on this we can say that our magnetic field will be in our minus K direction. And the option that are correct one is our option number A is correct, and option number C is correct. Okay. Option A and C are correct. Option A and C are correct. We have come to the next question, and here it says that it was asked in the year 2013 advanced question, and states that a steady current I flows along an infinitely long hollow cylindrical conductor of radius r. This cylindrical cylinder is placed coaxially inside infinite solenoid of radius 2r. The solenoid has n turns per unit length and carries a steady current I. Consider a point P at a distance r from a common axis. The correct statement is or are r. In this case we have a conductor, hollow conductor, and this hollow conductor is placed inside a solenoid coaxially, okay? And the radius is entirely different. So let us draw the, so let us suppose this is our infinite hollow cylinder, and its radius is given as r, and this is placed inside you can say a solenoid whose radius is 2r. So we can just draw a solenoid, something like this, and the radius of this solenoid, the axis, they are coaxial, but the radius is 2r, and it carries a current I. So we can merge these two figures and draw an equivalent one. So that can be approximately like this. So this is our hollow cylinder, and on this we can draw our solenoid, and they are coaxial. So this is our R, and the solenoid will be something like this, such that its radius comes as 2r, and it carries a current of I. Okay. Now in this case it says that consider a point P at a distance r from the common axis. And we can easily move the position of this r according to all these options. So the things which are given to us, it says that current, steady current I flows along infinite long. Okay, the current is also in the cylinder also. Okay. So both are carrying the same current, that is our I. And the current will be only on the surface of the, you can say, this hollow cylinder. You can say hollow cylindrical conductor. Its radius is capital R. Capital R. Current is our I, and that flows along the length of the cylinder. Along the length of cylinder. So we can say it will be flowing something like in this direction. It's not mentioned in here. And as it is hollow, so therefore you can say that current is only in the surface of the cylinder. Current is only on the surface of cylinder. So which basically means that for R less than capital R, that is the radius of cylinder, there is no current. So no current inside. Now we have the infinite solenoid. Now infinite solenoid, the radius is 2r. 2r, and so which basically means it completely encloses the cylinder. You can say so it encloses the hollow cylinder, and here the turns per unit length is given as small l. Turns per unit length, it is given as small n, and current is same as that of a hollow cylinder. Current is given as I, and this is same as cylinder, but I think that is sufficient for the time being. Direction as such is not specified in which direction the current in the solenoid as well as in the cylinder is flowing. So let us consider, you can say, the point P. So point P, it is mentioned that it has to be at a distance r from the common axis. At a distance r from common axis. So based on this, there are three regions which we are going to consider, or in the question it is asked. And the first region which is asked is our 0, r is greater than 0 but less than capital R. That is our, this point will be inside the hollow cylinder. Inside the hollow cylinder. Second, it says that the small r is greater than r but less than 2r. So this will be between the cylinder and the solenoid. Between the cylinder and solenoid. And the third one is when r is greater than 2r, and this is our outside the solenoid. Outside the solenoid. So let us try to find out what will be the magnetic fields that are involved in these cases. Magnetic fields involved. So let us say that magnetic field due to hollow cylinder let us call that as BC, and this BC we are going to so the hollow cylinder, it is BC, and it is said that it is an infinite cylinder with a current I. Therefore, inside the cylinder, that is R is less than capital R, as there is no current flowing inside the cylinder. So as per Ampere's law, we can say our magnetic field inside the cylinder or hollow cylinder is equal to 0. We can say by Ampere's law, since no current is enclosed, our magnetic field of the cylinder will be equal to 0. And second is our outside, and here outside we are only talking about the hollow cylinder, where this small r is greater than capital R, and under this condition this hollow cylinder behaves like a straight wire conductor, long straight wire. So it behaves like a long straight wire. Long straight wire at the axis. And we can write, under this condition, the magnetic field because of the hollow cylinder will be equal to mu naught I upon 2 pi r, and it will be tangential to the circles around the axis. Tangential to the circles around the axis. Now we come to the solenoid part. So magnetic field due to solenoid. Let us call that as Bs. So once again, we are, can say, inside the solenoid. Inside, where the small r is less than capital R, and in this case capital 2R rather. So therefore you can say our Bs will be equal to mu naught n times I, and it will be uniform and parallel to the axis. Uniform parallel to the axis. And now we have outside, that is R is greater than 2R. Ideal, for ideal cylinder, this will be equal to 0. Okay. So we have analyzed the hollow cylinder as well as solenoid independently. Okay. Now we are going to find out when they are merged together to form one single entity. Okay. So in part A, we are having for small r is greater than 0 but less than capital R. Okay. And for hollow cylinder, magnetic field was equal to 0, and for solenoid, magnetic field was equal to mu naught n I. So therefore net field, that is our B, will be equal to mu naught n I, and which is obviously not equal to 0. Now we come to the part B. In this case, R is greater than capital R but less than 2R. Yeah, so option number A is the correct one. Let me write it here. Option A is correct. A is correct. Now we come to the second part, and for hollow cylinder, we have magnetic field is equal to mu naught I upon 2 pi r, and it is tangential. And solenoid, is our Bs is equal to mu naught n times I, and it is axial. Therefore net magnetic field that is our B will be equal to the vector sum of BC and Bs. So we can write its magnitude will be equal to Bs square plus BC square. So this gives us that B will be, you can say, mu naught Ni whole square plus mu naught I upon 2 pi r and it whole square root. So at least based on this particular equation, we can make an approximate judgment that it will be neither purely axial, neither purely tangential. Okay. So it will be at some sort of angle. So we can say not purely tangential or axial. So we can write that it is at some angle. We can also find out angle if required. It is at some angle. So therefore, if you see the options, it says that it is along the common axis. So it won't be along the common axis. So option number B is incorrect. And it also says the magnetic field is tangential and centered around the axis. Okay. So this will be also, you can say, incorrect. So both options B and C are incorrect. Option B and C are incorrect. Now we come to the last option, that is our D, and it says that for r greater than 2r, and here a hollow cylinder is our BC, which will equal to mu naught I upon 2 pi r, basically means non-zero. And for our solenoid, which is our BS, it will be equal to 0. Approximately 0 if it's idle. Okay, let me put approximately. And therefore net field, that is why B is approximately equal to, for hollow cylinder, which is mu naught I upon 2 pi r, not equal to 0. And the options, that is for the final part, that is D, it states that it is non-zero. So option number D is also correct. Option D is correct. So this completes all the 4 questions. I think 3 questions rather. One was from 2013 mains and 2 were 2013 advanced. Thank you.